We're now going to tackle a different kind of application problem that requires the use of a rational equation. And this kind of problem we put in the category of calling it a distance rate time problem. And here's what the problem says. A plane flies 350 miles with the wind. In the same time, it can fly 310 miles against the wind. The plane has a still air speed of 165 miles per hour, and we're asked to find the speed of the wind. Now, let's be sure we're clear on what the 165 miles per hour represents. That's how fast the plane can go if there were no wind at all. It should seem reasonable then that if a plane is flying with the wind, that the wind will help its progress, and so its effective rate or speed will be more than 165 miles per hour. And in a similar way, when the plane is flying against the wind will inhibit its progress, and so its effective rate should be less than 165 miles per hour. So we'll hold that thought until we need it in just a moment. Now, you'll recall, I think, from earlier work that one version of the formula relating distance, rate, and time is distance is equal to rate times time. Now, you'll also recall that the first guideline in solving an application problem is to organize the information into what's known and what's unknown. Now, we could certainly do that in this case, but I think a little more efficient way to organize the information would be in a table or chart. So I've set up a chart here with 3 columns, and we have the 2 conditions with the wind and against the wind. And what we'll do is label the 3 columns with the 3 conditions that we know we must speak to. So we know the distance is equal to rate times time. Now, at least that's one version of the distance, rate, time formula. So now let's go to the problem and pick out what it is we know and put it in the appropriate place in the chart. Now we can see that the plane flies 350 miles with the wind, so we can place 350 in this box, and we're told it flies 310 miles against the wind. So we put 310 here. Now, what do we fill in for the rate or the speed for each of those conditions? Now, before we do that, we have to first, I think, define a variable here. And the variable that we need to introduce would be what the speed of the wind is. So we'll define down here pretty carefully. We'll say let x be the speed of the wind. Now, as we discussed a moment ago, when the plane is flying with the wind is going to help its progress. So its effective rate then will be the rate in still air plus the rate of the wind. So we can place in this box then 165 plus x. And when the plane is flying against the wind, it's going to hurt its progress or inhibit its progress. So its effective rate will be then 165 minus x. So far, I hope this is clear. Now, what do we fill in for the time blocks? Well, you know that one variation of the formula distance equals rate times time. If we were to solve this formula for time, or t, we can see that t is equal to distance divided by rate. So we'll simply take the distance divided by the rate for each condition and put it in the time column. So we're going to have 350 here, divided by 165 plus x. And for the second condition against the wind, the time will be then 310 divided by 165 minus x. So we've now filled in all 3 columns for both conditions. And now what we need to do next is to go to the statement of the problem to determine exactly what kind of equation we need to write. Now, if you go back up to the problem, you'll see that we're told that the time with the wind is the same time as against the wind. And here's the key phrase right up here in the problem, same time. So what we'll do then is simply set equal to each other the two expressions for time that we have in that last column. So setting the two expressions for time equal to each other that we saw from the previous chart, we have these two expressions, 350 divided by 165 plus x being equal to 310 divided by 165 minus x. This is a pretty basic rational equation, and you know from what we've done previously that we can solve this easily by simply cross-multiplying to eliminate the fractions. So we'll have then 350 times the quantity 165 minus x is equal to 310 times 165 then plus x. Next we'll distribute on the left hand side, and 350 times 165 turns out to be 57,750. Then minus 350 times x. And on the right hand side, 310 multiplied by 165 is 51,150. Then plus 310 times x. Now I think what might be best to do here would be to let's subtract 51,150 from both sides. So we end up then on the left hand side with 6,600. We have minus 350 x is equal to 310x on the right hand side. Now if we next add 350x to both sides, we have 6,600 then is equal to 660x. And if we divide both sides by 660, we'll find that x then is equal to 10. So that will be, if we want to express the answer then as a sentence, which is always a good idea to do. Being alert to proper units, we can say that the speed of the wind is 10 miles per hour. Now let's next check this result to be sure that we're correct. So to carry out the check, what we need to do is simply substitute 10 each place an x occurs in the original equation, which you can see that I've done here in red. And so the left hand side will simplify to 350 divided by 175. And on the right hand side, this will simplify to 310 all over 155. And simplifying each side of the equation, each turns out to be equal to 2. So we're assured then that the rate of the wind is indeed 10 miles per hour.